Alright, here we're looking at section 8.4, and our learning targets for today are identify even and odd functions. Then we're going to continue our graphing quadratic functions, but now we're going to be looking at this form. We've been dealing with standard form so far, but now we're going to be looking at, this is called vertex form. So I've got f of x equals a times the quantity x minus h squared, and that's how we know that it's a quadratic, because I have that exponent of 2. Then again, I'm going to be graphing quadratic functions of the form f of x equals a x plus minus h squared plus k. You'll see what this k value does. And then we're going to be modeling some real life problems using that vertex form. So first we're going to look at even and odd functions. So a function is even when f of negative x, so if I put a negative x everywhere I see an x, if this equals my f of x for each x in the domain, so that's when it's even. So what I always think about is the even functions are symmetric about the y-axis. And remember, the y-axis goes up and down. So for example, our original quadratics that we've been talking about that have my vertex at 0, 0, that would be considered an even function, because if I was to fold across this y-axis, I would end up with the same graph. It would overlay each other. So that would be even. So a function is odd if I put in a negative x value and the whole thing turns negative for each x in the domain. So what this looks like is that it's symmetric about the origin. So that means I reflect it over the x-axis and then I reflect it over the y-axis. So if I look at the graph of a line, if I was to reflect this piece, this top piece right here, over the x-axis, it would be down here, and then I was reflected over the y-axis, it would be down here, and it would lay on top of my original graph. This would be considered an odd function. So now let's determine whether each function is even, odd, or neither, because there's a possibility that it's a neither function. So the first thing I want to do is I want to rewrite my original function. So now I'm going to substitute a negative x, right, anywhere I see the x in my equation, and kind of simplify and see what I end up with. So now I can substitute f of x for 2x. And so now I see that I ended up with a negative the whole thing, right? So my entire function became negative after I plugged in this negative x. That means that the function is odd. So now let's look at letter b. Okay, so I've got my g of x equals x squared minus 2. So I write my original function. Then I substitute my negative x in anywhere that I see an x. Then I simplify and solve. And since I see that I ended up with the same thing, that tells me that it's even. So here, when we have an odd function, I end up with a negative of my entire function. That tells me it's odd. If I end up with the same exact thing, that tells me that my function is even. So now let's look at h of x. So I've got my 2x squared plus x minus 2. So I write my original function. Now I substitute this negative x everywhere I see an x, and then I simplify. So these are different things. So we see the only difference really here is I have a negative in front of this b term instead of this positive up here. Since they're different, I say that it's neither even or odd, right? So I have to get the entire function negative for it to be odd. The entire function has to be the same if it's even, and if it's not either of those, it's neither even nor odd. So try this, see what you can come up with, and see if you notice any patterns on some of these things. So here's our second learning target, graphing functions, quadratic functions of this form, a times the quantity x minus h squared. The biggest thing I need you to notice is that this always has to be a minus sign in here. And this is going to continue on. This is a form you're going to see for many different families of functions. And it's always going to be minus in here. Okay? So when h is greater than 0, and what that looks like is going to be something like, I've got my a value, so x minus 4 squared. See how even though I have this minus sign in here, my h value is 4. Okay, so h is greater than 0. It's a horizontal translation. Horizontal meaning back and forth. Translation meaning I just slide the whole thing. H units right of the graph. So since my h is a positive 4, it translates my graph to the right. So when my h is negative, so if I have my a times x plus, that's x plus 4 squared. I always want to get this to be a minus first, so I can rewrite it as x minus a negative 4. squared. So you see how now I have a negative and minus sign here, so my h would be a -4 in this example. So now that my h is negative, my h is less than 0, it means I'm translating to the left that many units. So what happens here is that my vertex is changed. And remember, the vertex is the point on the graph where it changes direction. So my vertex of the graph of this function, f of x equals a times the quantity x minus h squared, is h comma 0. So this value, this h value, tells me my vertex. And as long as I don't have anything else, that's going to be a 0, and we'll look at when this changes. So then again, just like we've looked at before, the axis of symmetry is always going to be this x equals the x value of your vertex. So here it's just going to be x equals h. So for this red example, since my h was 4, my vertex would be 4, 0, and my axis of symmetry would be x equals 4. So for my green example, with my h being a -4, looking like x plus 4 in here, my vertex would be -4, 0, and my axis of symmetry would be x equals -4. So I can use this h value to help me find the vertex and the axis of symmetry. So here I want to graph 1/2 times the quantity x minus 4 squared and compare it to my parent function. And here my parent function is just x squared, right? It's as simple as I can get. So first thing I want to do is I want to find my axis of symmetry. So first I look and I see I have a negative sign here, so I know that my h value is 4. And I'm going to go ahead and write that. So my h value is 4. I'm going to graph the line x equals 4. That also tells me my vertex point. So I've got that vertex, so because h equals 4, I have the point 4, 0. And then I'm going to plot 2 more points on the graph. I'm going to choose a couple values less than the x-coordinate of my vertex and a couple on the right side. So when x equals 0 and when x equals 2, you'll see that both of those are smaller, are to the left of this 4 value. So I just plug those values in, and I simplify and solve. So now I can plot these points as well. So I have 0, 8 and 2, 2. So then I can reflect those points. So we see my parent function in black, right? I've plotted my axis of symmetry, which was this black line, and I plotted my vertex, which is this point down here. We'll do that point down in green. So I've plotted my vertex and I've plotted my axis of symmetry. Okay, so then I picked 2 points to the left and I found these 2 points here. So then the easiest way that I can do is I can tell, well, how far away from my axis of symmetry am I? And here I see that I was 4 spots, right? Because each hash mark is 2. So I go 2, 4. So now from here I have to go that same distance. So 2, 4. Here's going to be that other spot. And I do that with my other point as well. So from this point to my axis of symmetry was 2. So again I go 2 and here's my next point. So now I have 5 points that I can just connect with my curve and I can compare them. So when I'm comparing this to my parent function, I want to say that they're both opening up, right? Because they both have positive a values. The graph of G is wider or shorter and fatter because I have this vertical shrink, right? Because it's less than 1, it's a fraction. So my axis of symmetry is now x equals 4, which is my h value. My vertex went from being 0, 0 to 4, 0. So it's a vertical shrink by a factor of 1/2 and a translation 4 units right. This sentence right here is going to be huge when we're comparing graphs, and we always want to compare using mathematical terms. So the biggest thing you're going to need to know is, how do I write a sentence that compares my graphs? So here's what I would say. The graph of G is a translation 4 units right and a vertical shrink by a factor of 1/2 of the graph of x. And you'll see that includes all the different values in my equation that tells me what's different. So now here's your next monitoring progress. See what you can come up with and see if you can tell right away without even graphing them what's going to happen to your graphs. So now here's our third learning target, and you'll see the one thing that I've added here is this k value. This k actually helps us with our vertex a lot. So this is called the vertex form. This is the vertex form of a quadratic function. So we've talked a lot about quadratics in standard form, so now we're going to be looking at vertex form. Okay, so the only difference between what we did on the last slide, we still deal with h moving it left and right. This k value is a vertical translation, right? It goes up and down. Okay, so the graph of my vertex form is a translation h horizontal and k vertically. What happens? So you'll see that whatever the value of k is, that tells me if I go up or if I go down, and that tells me how much. So let's look at an example. So here I have g of x equals -2 times quantity x plus 2 squared plus 3. So the first thing I notice is I have a plus in here, so I need to rewrite this so I can find my h value, which my h is going to be a -2. So then I can graph it. So first I want to do is graph the axis of symmetry, which my h value was a -2, so that becomes my line of symmetry. Then I plot the vertex. So to find the vertex, I find my h and I find my k. So my h was -2, my k was 3, so I plot that point. So now I find 2 plot points on the graph, and I picked just 2 values that are less than the x-coordinate of my vertex. So I picked -3 and -4. I substitute those values into my original function and get my answer. Then I have 2 more points I can plot. So then I just can plot those points and reflect. So here's the vertex point that I plotted, and here's one of the points that I found and the other point that I found. And again, I can reflect, so I count how many spaces over till I get to my axis of symmetry, and then I continue to go over. So these points are the same distance from the axis of symmetry. So now I can draw a smooth curve. So now I have to compare. Well, I notice my new graph is opening down. I also notice that it's taller and skinnier, right, because that is a vertical stretch, and I have a horizontal translation and a vertical translation. Okay, so that's what we're talking about here. So this last sentence, right, is our big important one. The graph of g is a vertical stretch by a factor of 2, a reflection in the x-axis that makes it open down, the translation 2 units to the left and 3 units up. And I can tell all of that just from my function up here. This negative tells me I'm opening down. The 2 tells me that it's a vertical stretch. This tells me my h is a -2, so I move 2 to the left, and my k is a 3, so I go up 3. So all of this can be told from just my function without having to graph it. But I also need to know how to graph it. Okay, so now we're going to look at our next example. So considering the function in g, we're going to be graphing this f of x equals g of x plus 5. Okay, so here my h is going to be -5. So my graph of f is a horizontal translation 5 units to the left of g. So to graph that, really I can take all of the points that I plotted for g and just move them 5 to the left, so subtract 5 from my x, and then I can graph my new graph. It's actually pretty simple. Once we have the main graph taken care of, I can just go ahead and continue to use my h value. And I knew that this was going to be an h value and not a k because it was inside my parentheses with the x. If it was outside here, then I knew it would be a k. So then it would translate it up or down. But here is an h value because we're inside the parentheses. So here are your couple monitoring progress. See what you can do with these. So now we're going to look at our last learning target, dealing with some real-world examples. So water fountains are usually designed to give a specific visual effect. For example, the water fountain shown, that we're going to see in a second, consists of streams of water that are shaped like parabolas. And remember, a parabola is a shape of a quadratic function. It's kind of like a U. Notice how the streams are designed to land on the underwater spotlights. Write and graph a quadratic function that models the path of a stream of water with a maximum height of 5 feet, represented by a vertex of 3, 5, landing on a spotlight 6 feet from the water, represented by 6, 0. So first I have to figure out what we're looking at. And I know what the vertex is, because that was given to me here, and I know another point on the graph, which is 6, 0. So then I am asked to write and graph a quadratic function that models that. So I can use those points and the vertex to write my function. So first I want to use vertex form, because I know what the vertex is. So I substitute in my vertex. I've got my 3 and 5, which is my h and k values. So now since I have this other point, I have to try and find what my a value is. I can use this other point as an x and a y, and simplify and solve for a. So I substitute those in. So then I end up 6 minus 3 is 3. 3 squared is 9. And then I can simplify. So I subtract 5 from both sides and divide by 9. So my a is a negative 5/9. So just to finish it, I just have to rewrite my function. So f of x equals negative 5/9 times the quantity x minus 3 squared plus 5 models the path of that stream of water. So now I can graph it. So again, I graph the axis of symmetry, which was at h equals 3. Then I plot my vertex, which I was given. Then I can find 2 more points, which I was already given a point at 6, 0, so I would use that one. So now I want to pick a point between 3 and 6, because those are the 2 x values I have, then find the corresponding value. They picked 4.5, and it doesn't matter which point you pick, it can be anything. So I substitute that in and solve, and now I can plot those points as well, and then reflect it across my axis of symmetry. So here's my graph of my function, and now I can look and see what it would look like using a graphing calculator to see how well I did, and then I can plot and find that those are my zeros of functions, but I knew that because I had solved for that already. So the big thing was to first find your a value, and then you can write your function based off of that. So now I want you to think, if my vertex is changed, my vertex is 3, 6, now try and write a different quadratic function that models this path, right? Because this tells me that it goes a little bit higher. So let's look back at our learning targets. First we had to identify even and odd functions, and that really comes into play if on this page, right? Because if I end up with a negative, my whole function is negative, that tells me that it's going to be odd. If my function doesn't change, that tells me it's going to be even, and if it's neither one of those, it's neither even nor odd. Then we graphed quadratic functions using the form f of x equals a times the quantity x minus h squared, where this h told me a horizontal translation. Do I shift it left or right? Then I looked at vertex form, and that's this right here. F of x equals a times x minus h squared plus k. Again, this h tells me a horizontal translation, left and right, and this k tells me up and down. It's a vertical translation. And then I looked at some real-life problems, and we're going to look at many, many real-life problems using this vertex form, because for a lot of problems it's a lot easier to graph and figure things out using the vertex form than it is using standard form, which we've done in the past. So now that we've figured out some vertex form and identifying even and odd functions, now I want you to go ahead and work on the homework for 8.4.